All right, hello again. I'm going to be doing another Leetcode question. We're choosing an easy one at random. We have a timer over here in the bottom right, so let's start the timer. And we've got number 69. We're going to do the square root of x. Oh, that's kind of fun. Given a non-negative integer x, return the square root of x rounded down to the nearest integer. The returned integer should be non-negative as well. You must not use any built-in exponent function or operator. For example, you can't use pow of x to the 0.5 or in C++ or x double pow to the 0.5 in Python. Yeah, that would be really nice. Okay, so one of the constraints we're given is that it's going to fit in integer space, so 2 to the 31 minus 1. It's always going to be a positive integer. That's nice to, well, it's always going to be 0 or a positive integer. I guess one question is whether 0 is considered positive or negative. That's an interesting math question. I think there's an answer for that, unrelated to this for now. So what we're trying to do is have some sort of function called, it looks like they call it my square root here. And we're going to take as input a int. And our output is also going to be an int. And it has to be, well, it should be non-negative. That makes sense. Any square root will be non-negative. And kind of what I'm thinking straight off the bat is there's kind of a approach using binary where you're just doing, well, I guess that's powers of 2, which is not exactly right. The square root of 8 is 2.8. So yeah, it's not dividing by 2 every time. So we don't want to do that. Never mind. For now. I think there might be some arguments for dividing by 2 over time, but that is not what we're trying to do. Instead, we're trying to find the rounded down nearest integer to that x. Well, we always know that the square root of a number is going to be less than half of it, I think. Is that right? So square root of 1 is 1, so that's not true for 1 or 0. So there's some special cases there. So if num is less than or equal to 1, return the number. We'll just keep that in mind. The other thing I'm thinking of is doing it the other way around. You could iterate through the numbers going from 1 or 2 until the number divided by 2 until you reach something that is greater than the number itself. And that would be kind of O of n for the n of the number. That's a very brute force approach. So let's just put that up there. We're not going to do it probably just yet. Brute force iterate 1, 2 to n over 2. Multiply and number by itself and see if it's larger. So that's one way you could go about this. This would be O of n for n equals number. Operations, that's pretty bad, even though it's 2 to the n over 2 range. You could modify this by doing something like binary search, where you square the number each time, and then as you get closer to it, once you pass it, then you kind of like a bisectional search until you find the number. So let's talk that one out. So the idea is you start at 2, check if the square greater than number. If not, like that, for keep doing it with new squared number until you do, and now you have your range. So let's just say 2, then we get 4, then we get 4 squared is 16, 32. Sorry, 16 squared is, I'm actually not sure. 256, is that right? 6, 6, 36, 10, 10, 16 times 16. Let's just quickly do that up here. 256. Okay, I wasn't too far off. I thought it was something like that. And so on. So that'll get us to O of log n to find the number when squared And then after that, you found basically the two values that are between whatever number. Let's say n was equal to, I don't know, 134, let's just say, you know, and we're trying to find the integer that is between, that squares to that value. So we know that 2 to the power of, 16 times 16 equals 256, and that's too big. And we also know that 4 times 4 is equal to 60 and too small. So we know that the answer is going to be somewhere between 4 and 16 is basically what we find out for the square root of n. And then you can just iterate through the values of that, and that becomes, and that range that you're iterating through is, I think, considered constant in space. That's considered O of 1 because it's, is that true? I guess not really. You could kind of do some sort of similar doubling thing here, but I don't want to get too stuck in the weeds on that just yet. Let's just think about whether there's some other way we can approach this before we go through this bisectional search. No other constraints. Not that we're doing this here, but another approach is having a table. Build a table ahead of time that maps all ints to squared ints. Then it's a O of 1 time to look in the table. And then O of technically 1, but is equal to 2 to the power 32 minus, well, 2 to the power 32 values, constant space. This is actually not a bad approach for some limited cases like this, but that is probably not the intent here. Good to call it out. I think kind of what I'm trying to think about is whether we want to always be doing the squares or if we want to do doubling the number. If there's any argument for doing that, it might be useful. Then I'm trying to see if there's some sort of mathematical approach finally. Like approach 5, math. There's almost definitely a mathematical solution to this that could be done without using the built-in exponent. It's probably how this function is written. If you guys already know this ahead of time and you're clamoring in the comments, please let me know. Sorry about that. I'll be interested to hear about it. I think doubling the number instead of squaring the number every time is actually the log of n. And I might be incorrect about squaring the number because that becomes yeah, doubling the number is log of n. Log base 2 at least. So squaring is a lot faster actually. And then if you were to double your way through that below there, you'd get them faster. So I think it's actually, this is faster than log of n, and I don't remember what it is. O log, or O n to the power of 1 over n? Or 2 to the power of 1 over n? Is that something like that? I might be completely off base here, so apologies if so. It's definitely one of those inverse exponential curves for big O, I think, for when you power the number every time. I think we're getting too stuck in the weeds, so let's just stick to a doubling based approach, and at least we can say that's log of n, and then iterate through the values between those two ranges otherwise. So the nice thing about that one is we can just use binary right shifts and left shifts to get the number doubled every time, and I think that'll be kind of nice. All right, so the way we'd like to do this is we'll say our lower left value is going to be equal to 2, and then we don't know what our right is yet. Okay, so while left times left is less than the number left plus 1. So basically, oh no, left right shift by 2. And how do we do the right shift? Is that how it is? Right shift by 1, which is actually, let's just to make this clear, equals left times 2. I think you can rewrite this as binary right shift by 1 or something like that. So we'll just double it every time. Left shift. I think this is the way we want to do it if we were to be doubling the value. So every time, while the number is less than the num, we're just doubling it. And this will be an O of log n to find the larger number. And then, once we found it, and then while we're trying to find the integer rounded down to the nearest integer that reaches that value. So actually now, while left times left is greater than num, left minus 1. And then we return that value because now we have a integer doubled closest to squared, to num when squared, but less. So while the left by left is less than or equal to num, greater than num, we subtract 1. Once it becomes equal or lesser, we're done. So that's the key point. Not greater than or equal, want it if it's the same. So let's actually just think about the logic here for a second. We could even start with 1 just to be clean. The reason I was wanting to start with 2 is because I was going to go with the squaring approach. So we're not actually doing the squaring approach, even though I think that might be better and might be how the square root, how this system works. We might get back to that in a second. We're going to do 32 and so on until we reach our value. So in fact, in this case, 128, 256, and that's kind of how we're doing it. And it stops at this number, and so it knows that the answer is going to be somewhere between, actually it's still between 4 and 16. So 8 squared is 64, so it'll actually be between these two. And it'll iterate from 16 going backwards until, in this case, it hits the number, which might be, I don't know, 9 squared is 81, 8 squared is 64, 10 squared 100, 11 squared 121, so probably 11 is going to be the answer. And 12 squared 144, yeah, so 11 squared equals 121, 12 squared equals 144, I think. So the answer is going to end up being 11. So it'll find it in that range. Because 12 squared would be too big. Similarly, let's go and do this here. Let's have a look at this approach before we check. We're about 13 minutes in, so that's more than enough time. Let's try it with example 1. So x equals 4, and we expecting 2. So we are set num equals 4. What do we get when we get that in? Num is not less than or equal to 1, so we continue. So right now, left is equal to 1, and while left times left is less than num, so right now it is, so we double it. So left equals 2, and 2 times 2 is equal to 4. 4, so we break out, and now we're here in this part. And so we check if 2 times 2 is greater than 4, and it's not, so we don't subtract anything, so we just return 2. And we're good to go. So I think that should work. So let's first of all bring this all down. And hopefully you all can see this still. Okay, good. Okay, so I want to just copy this over and see what we get. And can you guys see this? Yeah, good. All right. Unfortunately, I need to remove all these extra tabs. And this is kind of a two-pass thing. We double until we get to the right, and then we iterate while we go to the left. O of a range. Does it become O of n at this point, actually? In the worst case, you've doubled a really large amount. Technically, you could just keep doing this doubling every time going left. So I'm interested to see if this is a O of n or O of 1. I think it might be O of n, actually. So in the worst case, we get a O of n based solution, which is similar to just iterating through the whole list. So we might have to come back to that. Let's do a quick run and see how this does, first of all. Oh, and the number is x, so let's just replace that. All right, it gives the right answer for these small cases. I'm interested. This is actually a good case of where this might be, if it's inefficient enough that it's O of n instead of O of 1, I would expect this to take a lot longer on the solution space. Yeah, it does, than the best solution. So we're missing something here. I wonder what that is. I think it's got to be this pit right here. So let's have a look at this and see if we can do something better than iterating at this point. What I'm thinking about now is, instead of iterating by -1 each time, we want to subtract a value that's doubling every time. And this goes back to our bisectional search right here. So one way you could do that is squaring the number every time in one direction and then doubling the number down in the other direction. Is there something better that we could do there? Can we start in the center, like n divided by 2, and then, instead of actually doing what I'm doing here, I think we should do a bisectional search. So this was pretty slow. We're going to call this kind of a brute force. Approach 2.1, double, then iterate, brute force. It's good to have a solution, but I think we can definitely do better than that. So what I'd like to do is a bisectional search. Instead, we start at n over 2, check if it's bigger or smaller, larger, smaller, and then if it is, we just either divide the number by 2 or increase the number by 2 each time. And I'm not sure exactly how I want to do that yet, so let's just think about that. So if the number is less than or equal to 1, return the number. Otherwise, left equals the number divided by 2. And we're going to use double slash because that gives us a truncate, rounded down, divide by 2. Center. Or let's call this, left still. And what I'd like to do now is check if left times left is less than the number. Well, first of all, if the left by left is equal to the number, we just return that. We're good. Found the whole square root. Otherwise, if the difference between the squared number and the goal number, we can actually use that distance to make some decisions, can't we? What I'm trying to think about here is, let's say we have our n is equal at 134. If we take half of that, that's what, 75, 76, 77? Equals n over 2 equals about 77 in this case, or is 77. We take 77 squared is much greater than n. And in fact, it's a really large number. I feel like we could do something about that. So then we take the halfway point between the left and 0. Something like that, and now this will be whatever 77 divided by 2 is. 35 is, 40, 39, 38, I think, or 37. So that's 60 plus 14. Wow, sorry, I'm having a hard time with just dividing this by 2. That should be 35 plus 3. So 38. So that'll be 60 plus 16, so 76. Yeah, and then the next one would be too large, so 38. And it does the same thing again. So let's see, 38 times 38 is too big. Greater than n, which is 134 in this case. And we kind of keep doing this, and actually let's just go ahead and do it right here. So again, left equals 0 plus left divided by 2, and that equals to half of 38, so that'll be 15 plus 4, so 19. The same thing applies again. Left equals that, so half of 19. So we're doing a log n approach here. I just want to make sure that this approach will get us to the right answer on the other side too. So this will be 9, and then 9 times 9 is equal to 81. So, and this is less than n. So now we get the left is equal to the other way from our previous two values. So what we're trying to do here, this is the interesting part. We take left plus the previous left, which in this case would be 19. So we need to keep track of the last left and go halfway between those two. Yeah, that's how we want to do this. So 9 plus 19 is 28 divided by 2 equals 14. And 14 times 14 is greater than n. And we're almost there. So we go to the now we actually have something besides 0 here. We have the previous largest value, which was 9 plus left divided by 2, which equals 9 plus 14 divided by 2, which is equal to 23 divided by 2, and that'll give us our number we're looking for. That should be what? 11, I think. Yeah, 11, 22. And 11 times 11 is equal to 121, which is less than n. But it is the right answer because we know the next biggest number will be too big. And how do we make that check? So this is the logic I'd like to do, because this becomes an actual log n approach search. Okay, so I like that a lot actually. So left is equal to that number rounded down, and actually the way we want to do this, left equals 0 and right equals num. Actually num over 2. Is definitely going to be less than the n over 2. Square root will always be less than the half the value, except for when it's 1. When it's 2, square root of 2 is 1 in this case. Yeah, okay. And these are inclusive. And so center is equal to left plus right divided by 2. And now what we're trying to do is check if that value is equal to the num. If so, we have found it and we can return. Otherwise, doubled equals center times center. So now if doubled is equal to the number, we return it. Otherwise, if doubles is greater than num, then our new right is equal to center. And then else doubled is less than center. Left equal to center, and we continue the loop. And we'll do this until left and right are equal within one of each other. Oh, sorry, 1 second. Okay. Just got a text. Okay, I think this is the right approach. I just want to make sure we can end it properly. So what I'm trying to do is, let's make sure it's spelled right. And then at the end we return center at some point. So we do this while something, we're trying to kind of keep iterating until we have found the number or the left and right difference is equal to 1. Is that what it is? Let's see. So right now, we need to change all these words to a different. So right here, left is 9, right is 14. And center is equal to half of that. And that is actually the right answer, but we don't know that just yet. What we could do is do a check to see if the number if the doubled equals num or center plus 1 times center plus 1. Or it straddles a number is what I'm trying to say. Like, I don't know if this is the best way to do it, but the idea here is if doubled is less than num and next doubled is greater than num, we've found rounded square number, and we just want to return that. So let's actually put that in there. I think that'll be an end that we find, else if doubled is less than num and next doubled is greater than num. This is still technically O of n, so the whole thing becomes a O of log n type solution. I think we could also do another way we could do this is just check that if left and right distance is less than 1, while right minus left is greater than 1, for example. Once they become the same value or within one of each other, we're done, and we should just return that center because we're there. So let's have a look at this. I think this should be faster. Oh. Because now we've gone from a O of n based solution to a O of log n. So let's get that all put together. I think doing this doubling thing I'm not entirely sure about. This might be extra work that is overall slower. Okay, how does this look? Does this work for, let's say, the number 4? So 4 divided by 2 is 2. 2 minus 0 is greater than 1 because it's 2, so that's fine. Center is equal to 2 and 0. 1, center is 1. And yeah, no, 1 squared is smaller than the value, so doubled is not equal to the number 4. And 1 squared is 1, which is less than 2 squared is 4, and so it's not greater than that number. Or if next doubled equals num, we just return center plus 1. That's another little thing because we're doing this work anyway. If it was 5, or yeah, well, let's try this and have a look and see first. So it passes the 2 test cases. That's good to see. Let's see how we're looking in terms of the actual solution. Cannot access local variable center. Oh, am I reusing center incorrectly? Yeah, I guess that's fair. So we do actually reach a point. Oh. When it's 2, we get an output of 0 because 2 divided by 2 is 1. 1 plus 0 divided by 2 is 0. Center is 0. And that is... obviously not the case. We would expect the square root of 2 to be 1. So why didn't it actually return? So center is equal to 0. 0 squared is 0. 1 squared is less than. So we set the right to center when doubled is greater than left center. So I guess in this case we actually need to be careful when the number is equal to 2. Because it doesn't work in that case. Sorry about this. It's kind of interesting. Yeah. Okay, no. The logic is broken somewhere around here. When x is 3, we're getting an output of 0 when we expect 1. So let's work our way through this real quick. Left equals 0, right equals 3 divided by 2 equals 1. And we expect the answer to be 1. But because right minus left is not greater than 1, we're just returning the center. So actually it's maybe ending a little bit too early. I think that might actually be one of it. Let's just see for a second. Still running. Ooh, we ran into infinite loop with this. Okay. That was no good. So let's think about what's going on here. Left is 0, right is 1. Center is equal to halfway between the two of them, rounded down, so center equals 0. What do we actually want to do, and the number is equal to 3. Answer is going to be 1 in this case. And so right minus left is greater than or equal to 1. Center equals to that value. Doubled equals 0. Next doubled equals 1. And neither of those is equal to 3. So we pass these first two. And we've also checked that doubled is less than num and next doubled is less than num, so not this one either. So now we check if doubled is greater than num, which is not. So what we do is we set the left to center, and center is 0 and left is 0, so we get into infinite loop. Okay, so there's kind of our problem. We need to have a special case when the difference between left and right is... Would this have worked better if we hadn't started at halfway between 0 and 3? So what happens if we had started at 3? If we had started at 3, center would be 1, and it would have gotten to the right answer in that case. So maybe it's better if we start at that. And that handles the small number cases, and it only adds one more into the loop. So yeah, there we go. We're back into the fastest solutions approach. So that's good to see. This is the log n. I made a couple mistakes here, which I think is something for me to work on actually. You'd want to kind of check these edge cases a bit better, especially the while loop. Technically, we could have done a while true, because we should never reach this. We could also simplify this by either getting rid of these doubled thing, and in fact, let's have a look at that. We're at 33 minutes. We have solved the problem 2 ways so far, but I think it's important to get it a little bit cleaner. So let's get rid of this next doubled concept and see if we can just use this. And now we should return small enough. So we're just basically doing a bisectional search left and right. We're checking doubled. If it's equal to the number, we return it. If the doubled number is greater than, we set the right, otherwise we set the left, and we keep dividing down. And we do it until the distance between the two of them is greater than or equal to 1. Yeah. However, this could also reach an infinite loop. In fact, I'm starting to see that right here. Yeah. So what I'd like to do is, let's say num is equal to 3, answer, sorry, 8. The answer is going to be, I think 3, because 3 squared, or 2, because that's the closest rounded down square of 8. So left is equal to 0, right is equal to 8, center equals 4 in this case. So what I'd like to happen is it realizes 4 squared is too big. So left equals 0, right equals 4, center equals 2. 2 times 2 is equal to 4, which is less than 8. And at this point, we set our left. So left equals 2, right equals 4, center equals 3. 3 times 3 equals 9, which is greater than 8. So now we've set our left equals 2, right equals 3, and we should be breaking at this point. And then we return, well, why didn't we break at this point then? I would have expected to break instead of looping indefinitely. And what I'd like to do at this point is return left, I actually suppose, instead of center. Okay, so let's think about this. Left is 0, right is the number. We're hitting a infinite loop, I think, at zero and 8. Center becomes 4. 4 squared is 16. It's not the number. 16 is greater than 8. So right becomes the center. So right becomes 4. 0 and 4. Now the new center is 0 plus 4 divided by 2. 2. Center is 2 at this case, which is less than 8. So left becomes the center. Two. So then that goes to 3. All right, why are we having trouble here? This may be extremely obvious to some of you all watching, so sorry in advance, but sometimes it'd be like that. All right. Center is 3. Double is greater than num, so right becomes 3. And now right minus left, 3 minus 2 is greater than or equal to 1. Is it possible that right becomes smaller than left? And then we have a negative number that keeps expanding? That might be the case. Why is that? What we could instead say is while right is greater than left plus 1, that should at least handle the left being bigger than the right. I think that's... All right, so let's have a look at that and see how that does. Great, good to see. Yeah, so this cleans it up a bit. It was really that little bit right there. Right minus left divided by... right minus left greater than or equal to 1. So I think we had a situation where the right value was being set to a smaller number than the left. And then we kept reducing that one smaller and smaller until it got to 0. So, and once it hit 0, it was just an infinite loop. All right, good to see. This is a little bit cleaner. I think this is actually what I like the most. This is just this is called a bisectional search. Kind of get used to this kind of concept. It's been quite a while, so as you can see, I'm rusty with this, but I think from now on for the future problems, I should have this pretty down pat. Kind of good to get to this. Either way, we're 40 minutes in. If you're still here, thanks for watching, and I see you guys next time.